Hello, welcome to today's video where we're taking another look at vectors, specifically today looking at something called the cross product. But wait a minute, doesn't the word product mean multiply? Does that mean we can multiply vectors together? Well, no, not in the traditional sense at least. And in fact, if you were to write either of these two things with vectors, then that would be a bad idea. In fact, don't do it at all, because it's what we call ambiguous notation, which means that whoever's reading these two things won't be sure exactly what you mean when you write them, so therefore we don't write either of those two things. Which is a bit strange, because when it comes to multiplication with numbers, we actually have a lot of flexibility in how we notate it. For instance, if you want to write 2 times by 3, you can write 2 with a cross followed by 3 to mean 2 times by 3, or you could write 2.3. And different people prefer one or the other of those two notations, but they both mean the same thing. And in fact, it gets even better than that, because if you're dealing with algebra letters, you don't even have to write a symbol at all. You can just write AB to mean A times by B, which is really nice and convenient. However, with vectors, it's unfortunately a little less clear cut, and hopefully you're already aware of that because of the thing called the dot product, which is something that kind of takes the place of multiplication, but we have to notate it by writing the two vectors with that dot in between them. Of course, as we've just pointed out, the dot normally means multiply when it's applied to just two numbers, but when it's applied to vectors, it has this very specific process attached to it that hasn't universally been defined as the single way of multiplying vectors together. And there's a big clue in what I just said there as well, because the whole point of this is there's an alternative way we can combine two vectors that also kind of holds a role similar to multiplication, which is the cross product. And it's called the cross product because if the dot product is written with two vectors with a dot in between, then the cross product is written as two vectors with the cross between them for multiply, but in this case it doesn't directly mean multiply in the traditional sense. But what does the cross product actually do? Well, a partial clue comes from the alternative name for these individual products. For instance, the dot product's alternative name is the scalar product. And it's called that because when you combine two vectors using the scalar product, you get a scalar, which in other words means a single number. For instance, if you would do 321 dotted with 654, you would get this, and then that would get just the number 32, a single number, therefore a scalar. Whereas the cross product is sometimes alternatively called the vector product because if you do the cross product between two vectors, you will always get a vector. So that's one of the main differences. The result you get is in a different format. But how do we actually find the cross product between two vectors? Well, good news. If you look in the form booklet, one of the first formulas you'll come across in the vectors section is that A cross producted with B is equal to the magnitude of A times by the magnitude of B times by the sine of the angle between the two vectors times by the vector n hat. Of course, the hat notation signifies that it's a unit vector, which basically means it's a vector with length of 1, and then the n is to signify that this is a vector that's normal to the other two vectors. In other words, vector n is perpendicular to both vector A and vector B. But how do we find n hat? Well, that's a very good point to bring up, and in fact, I must tell you that at A level, we don't really ever actually use this formula in its direct format that you can see here. And that's because all the things, although linked in this nice way, are all things that are individually easier to find using other methods. So, although we'll come back to this formula in a future video because it's useful for something else, for now, most of the time when you're doing the cross product, you don't use this formula to find the cross product. And instead, you use a different formula which says that if A and B vectors are defined as A1, A2, A3 and B1, B2, B3 respectively, then as a result the cross product of those two vectors will be defined as the determinant of a 3 by 3 matrix, where the top row of that matrix is just the letters I, J and K to represent the I, J and K directions. The second row in the matrix is just the vector A written out going across, and then the third row is that second vector, so the elements of B written going across. If you work out what that is, that result will give you the cross product of A and B. Some people alternatively prefer to use this formula here, and that effectively just does the same thing, but at the same time just directly tells you where to put the A1, the A2, the A3, the B1, the B2, and the B3 in their respective places to just instantly find the cross product. And the good news is, all these formulas are in the form booklet. However, therefore, that does lead to an interesting thing. Some people do prefer to use the bottom formula, but because of the fact it just appears like a random arrangement of all these letters in a particular way, then people who want to use that formula end up always having to reference it from the form booklet in order to do it. Whereas I personally prefer to use the determinant of a matrix method, just because that's a method that after doing it a couple of times means you don't even have to look at the form booklet in order to know what the process is going to be, and therefore that's easier to remember, because ultimately you're already expected to know how to do the determinant of a 3x3 matrix anyway, so if we're just reusing those skills again here to help us do this thing, it's just more efficient for memory, and therefore ironically quicker as a result, in most cases. However, one more thing to point out before we launch into an example is, why do we actually care about finding the cross product anyway? Why do we supposedly have more than one way of multiplying vectors together? Well, it's because the cross product has a very useful result that we can use to our advantage in other areas of the vectors chapter, which is that if you do the cross product of A and B, then the result of that is going to be a vector that is both perpendicular to the vector A and is also perpendicular to the vector B. So just finding the cross product of two vectors will give you a vector that's perpendicular to both of the vectors you took the cross product of. There is admittedly one tiny exception to this, but we'll deal with that in a future video, and all I would say is the vast majority of the time this fact is true. So with that all out of the way, let's finally get into an example. And we're doing the cross product of the vector 321 with the vector 654. Something else worth bearing in mind is the order in which the two vectors are originally written does matter. So the fact it's 321 cross product with 654 is a different result to 654 cross producted with 321. So the fact they're written in this order does need to be paid attention to, because if you're using, for instance, the method I said I preferred, which is the 3x3 matrix method, we write I, J, and K, and then we write the first of the two vectors that was written out as the second row in our matrix, and then the second of the two vectors has to be the third row in the matrix we're writing here. And now all we've got to do is find the determinant. Of course, to find the determinant of 3x3, cover up a row and column. Always makes sense to pick the top row with these particular things if you're using this method. So picking the top row, that means we're covering up the IJK and the 3 and the 6. So therefore it's going to be the 2 times by the 4, which is 8, times by 5 take away 1, which is the other diagonal of course. And that's going to be multiplied by the element we covered up the row and column for, which was the I. So this is telling us how many lots of I we have. And then, of course, because it's the second element in the top row, we're then going to subtract j lots of the determinant of 3164. So that's 3 times by 4, which is 12, take away 6 times by 1, which is 6. And that's how many lots of j, as I already said. Then lastly, covering up the row and column with k in it will tell us what we've got to multiply k by. So that'll be 3 times by 5, which is 15, take away 6 times by 2, which is 12. That's how many lots of k we have. Now, with the I, J, and k, it's worth pointing out, therefore, the way I've written the result means you'll get a vector in IJK form, but you are welcome to alternatively write this out in column vector form if you're confident with this stuff. So it doesn't really matter which of the two you decide to write. So this would have been an alternative way of writing this stuff out. As a result of that, you will then simplify to get that we've got 3i minus 6j and 3k. So therefore, that is how you find the cross product between two vectors. Nice! And after that, for the sake of completeness, I must acknowledge that there is a way you can work out what direction the cross product vector is going to be going in comparison to the original vectors of A and B, using either your left hand and right hand and labeling your fingers in a certain way to be able to work out what direction that particular vector is pointing in. However, due to a mixture of the drawing of a human hand that I've done being absolutely horrendous, and also the fact that you don't really need to ever really do this for the sake of A-level exams, I'm going to move on from this swiftly and say we're not really going to be ever using that, because there's always a way that you can do numerical checks to know what you've calculated and how that fits in with everything else you've got in the question. So, that's all I wanted to cover in today's video. I hope you found it useful, and we're going to be looking at future videos what we can do using the cross product. See you in one of those videos. Goodbye.